Hi again, this is Hassan Korani. In this video we are going to continue our chapter about equations of straight lines for grade 10. Well, in the previous video we made a revision, as you know, about equations of straight lines studied in grade 9, and we saw the concept of a direction vector of a straight line. Now we will see the forms of equations of straight lines. Let's consider our study in an orthonormal system OIJ. An equation of a straight line D, the equation of a straight line D, has three main forms. What are these three main forms? The first form is called the reduced Cartesian form equation, which is y equal ax plus b, which we studied previously. The second form is the standard Cartesian equation, which has the form of dux plus vy plus w equal to 0, where u, v, w are all real numbers. This is the second form. The third form, which is called the system of parametric equations, which has this form x. We have a system of two equations, x equal alpha t plus x1, y equal beta t plus y1, where alpha, beta, x1, y1 are all real numbers. With t, we call it usually parameter or for this reason we call this system of parametric equations, which we will discuss in details later. Okay. The first form, the reduced Cartesian equation, which we know and it's familiar for us, which is y equal ax plus b, as we said before, where a and b are two real numbers. Now, a direction vector of D, as you know, in systems, in orthonormal system, usually a vector has coordinates. The coordinates of a direction vector of D is just 1a. You have to memorize it. 1 and a. A is the slope of the straight line. It's always 1 with a. This is a direction vector. Recall a is the slope of D. B is called the y-intercept, as we saw before. Okay, let's see an example or examples. Determine two direction vectors of the given straight lines. Let's see the first example. The reduced equation of a straight line. This is a reduced form, y equal ax plus b. As you see, we need to find a direction vector. As we saw previously, let S be a direction vector. We have here a equal to, and as a rule, a direction vector directly from the equation we can determine it. S is 1a, so here a is 2, thus a direction vector is 1, 2. But we are asked to find two direction vectors in order to know another direction vector. As we saw previously in a remark, that if this is a direction vector for D, we can easily multiply this vector by any non-zero real number. We call it previously k. Here, let's multiply S by 2. As you see, multiplying it by 2, we will get another vector S prime, whose coordinates will be 2 times 1, 2, and 2 times 2 will be 4. And this is a new vector, also considered as a direction vector, and by this way we can find infinitely many direction vectors. Okay, let's see another example. Straight line L, whose reduced Cartesian equation, y equal minus 4x plus 1, and try to find a direction vector. As you know, the rule says if it is in the reduced form, the direction vector is 1a. Here a is minus 4, then v, if we let v be a direction vector, then a direction vector will be 1a, 1 minus 4, And by the same way as we did before, we can find as many as we want direction vectors by multiplying v. Let's say by here I multiplied it by -3. We will get -3 times 1 -3, and -3 times -4, which is 12. So this is another direction vector also for L. Another example, the straight lines. As you see, dx equals 3. This is an equation of a straight line. As you see, when x equals constant, this is a particular case, this straight line will be parallel to what? It will be parallel to y-axis, and it's a vertical straight line. And we look for a direction vector for this. And also here we look for a direction vector for this straight line whose equation is y equal -2. As you know, y equal -2, a particular straight line which is parallel to what? In fact, parallel to x-axis, which is a horizontal straight line. Now, let's see the solution, direction vectors. D is parallel to y-axis, thus a j, which is a known vector in orthonormal system yj, j, whose coordinate is 0, 1, is a direction vector for D. And also we can multiply j by any number to get k, any number k, to get 0k is also a another direction vector for D. As you notice, if this is a vertical straight line parallel to y-axis, it has no slope. And D prime parallel to x-axis, similarly, we can notice that it's a horizontal straight line, and I will be a direction vector. We don't say the direction vector since we have many of them. And multiplying I by any real number k prime, non-zero real number, we will get another direction vector. And since it's horizontal, its slope is 0, as you know. Now let's see the standard or a standard Cartesian equation. The general form is ux plus vy plus w equal to 0, where u, v, w are real numbers. Non-zero simultaneously means non-zero at the same time, since if they are all 0, then we get no equation at all, and this has no sense. In fact, a direction vector directly from the equation of this straight line is, as a rule, we have to memorize it as has coordinates -vu, where v and u, we can pick them out from this equation. Let's see the slope now for the straight line. It's also a rule, the slope must be the ordinate of a direction vector that we are given over the abscissa of a direction vector. And this is also a rule, we have to memorize it. Examples: find a direction vector and the slope of d1 of equation 4x plus 3y minus 1 equal to 0. As you see, we have a standard Cartesian equation. U equal 4 and v equal 3, w equal -1. We don't care about w, we don't have it needed now. Then a direction vector, as the rule says, minus vu, it's -3, it will be -3 u, so it will be -3, 4. This is it. This is the direct direction vector. Directly from the equation we can find a direction vector by using these rules. And the slope, as a rule we said before, it's the ordinate over the abscissa. It will be of a direction vector, sure. It will be 4 over -3, which is -4 over 3. Let's see another example here. X minus 5y plus 2 equal to 0. It has the form of ux plus vy plus w equal to 0. Here u equal 1 and v equal -5 and w equal 2. We need just for to determine the a direction vector, we need the values of u and v. As you see, the rule says it's -vu and v equal -5. So minus v will be 5 and u will be 1. So the direction vector will be 5, 1. Clear? Minus v, this is minus v, so it will be 5, and u, this is it. And this slope will be always a direction, can be determined from the direction vector. It will be ordinate over abscissa of this direction vector. It will be 1 over 5. This is it. Okay, let's see the third form of equations of straight line, the system of parametric equations of straight line, which is somehow new for us. From its name, it is a system of two equations. It has this form: x equal alpha t plus x1, y equal beta t plus y1, where these red letters are in fact represent real numbers. T is called this number, this value, this parameter, this variable is called real parameter. We will see why when we make the proof for this form. A direction vector of this straight line, as a rule, is S alpha beta, where alpha comes from the coefficient of t in the x equation and beta coefficient of t in the y equation. And the slope will be the ordinate of, as previous case, ordinate of direction vector over the abscissa of direction vector. Okay, what about x1 and y1? In fact, x1 and y1 will be the coordinates of a certain point, given point on the straight line, and alpha beta represent the coordinates of a direction vector. Okay, let's see the proof of this this form. How did we get this form? This proof helps to understand the form of parametric equations. Let's say we have a straight line passes through a given point a, x1, y1, known, of known values, coordinates, and direction vector s alpha beta, also known. We have this, if we use this graph, we have a direction vector and we have a given point. Usually, if we let m be a variable point of coordinates xy, variable point on this straight line, we can notice easily that as m describes this straight line, the vector am and s are always collinear. Collinear means leads to say that am equal ts, am equal ks, or whatever. This number, usually a certain number according to the position of m. This comes from the collinearity of am and s. Thus, as you see, these two vectors are equal. ts and am are equal vectors. For this reason, we know that two vectors are equal, then their coordinates will be equal. Then abscissa of mx minus xa, x minus x1, equal abscissa of s times t, which is alpha t. And we will get the ordinates also of these two vectors will be equal. This leads to say that y minus y1 equal beta t, which can be written in this form: x equal alpha t plus x1 and y equal beta t plus y1. This is the result of our work, and this result, they call it system of parametric equations. T is called usually real parameter. Real since it's a real number, and parameter it's variable. Okay, x, y in this equation, in this system, sorry, represent coordinates of any point of D. X and y, they are, as you saw, x and y are coordinates of M, which is any point on D. Okay. Example: a straight line L defined by x equal minus 2 plus 1, y equal 3t minus 4, where t is a real parameter. We have here alpha equal minus 2, beta equal what? 3. So a direction vector, as a rule, alpha beta. So it will be minus 2, 3. Okay? And the slope will be similar to what we said before. It will be the ordinate over abscissa of direction vector just obtained. It will be 3 over negative 2, which is minus 3 over 2. Okay? particular cases, if a straight line has the form x equal t, x equal constant, and this is a general form, reduced form, then in parametric form we can write it in this form: x equal 2, it keeps constant, while y, since we don't have y, as you saw in graphical discussion before, y is in fact variable. This variable we let it to be t or k or whatever letter you want. This parameter, this variable is called parameter. Okay, this is the parametric form. Okay, and as x equal t 2, then this straight line will be vertical straight line, and j 0 1 will be a direction vector and has no slope. Let's see another case: y equal -5. Y here is constant, and we keep it constant with the same constant here. But x, in fact, which doesn't appear here in this equation, we put it to be a parameter. The parameter, we may call it k or something else. Okay, this is till now how to do a graphic representation of a straight line. In general, we draw a straight line, we need 2 points, as you know. In reduced case, we simply give x any 2 values to get y, and we get 2 points: 0, -1, 2, 3. Do them briefly since you know them. In standard equation, also similar to reduced case, we give x or y any value to get the corresponding values. By letting x to be 1, we can get y equal, it will be 2y equal -6, so y will be -3, and we let x to be, let's say, -5. If x is -5, 2y will be 0 and y will be 0. These 2 points help to draw easily the straight line L. While in parametric form, this is a different case. We can't place x by a certain value. We may, but it's easier to us to replace, in this case, the parameter by any real number and replace it here and there to get x and y. How? If we let t equal to 0, let's say in this case, in this example, if t equals 0, then x will be 2 and y will be 1, and this is a point belongs to D. We need another point by we can get it by replacing t by another value. Let's say t equal 1. For t equal 1 here, x will be 3 and y will be -1, and these are 2 points. Well, this is the end of part 2. Thank you for watching, and see you in the next video.